Hello students, welcome to Chemistry at JP's Academy and I am Nitin sir. Students, in today's lecture we are going to start with a very important and interesting chapter in physical chemistry, which is states of matter or gaseous state. Students, this chapter is very important from a JEE NEET perspective and also lays a foundation in understanding how matter behaves in different physical form. In the first lecture, students, we are going to start with understanding the different physical states of matter. Then we will further move on to intermolecular forces and understanding thermal energy. And then we start with the gas laws. Students, I want you to like, share and subscribe to the channel. So without any further ado, let's start the lecture. Students, we know that the different physical states of matter that we have solid states, then we have liquid, and then we have gaseous state or gases. However, there are two more which we do not really study, but there is also something called as plasma, and we have something called as a Bose-Einstein condensate. If anyone really knows what is plasma and what is Bose-Einstein condensate, I want you to please leave a comment behind. Now students, how do these physical states depend on, let's say, temperature is, let's say students, if we say that from a room temperature point, if the melting point is below the is above the room temperature, in that particular physical state the element will be in solid state. If the melting point is below the room temperature, then that particular element will be in liquid state. And if the boiling point is below the room temperature, then that particular element will be present in gaseous state. Plasma, students, on the other hand, you can say is superheated gas or gas at a very high temperature. And Bose-Einstein condensate is at very ultra low temperatures. What happens is that atoms they combine and they act as a unified, a giant atom or a super atom. That is what is Bose-Einstein condensate. So now students, let's first understand the different characteristics or different properties of solid states, liquid state and gaseous state. I've already written down the points for you students, so let's take these points one at a time. The first property, student, that we have is the arrangement of particles. Now students, we know that in solid states the particles are tightly bounded to each other in the form of a crystal lattice. The entire physical form of solid state, students, the physical state which is solid state, you will study in the chapter solid states in detail. Then we have liquid state. So we can say that in liquid state particles are arranged, however the range of arrangement is very small, whereas in gaseous state there is no arrangement of molecules at all. Second, we have shape. So we know that students, solids have a definite shape. Liquids and gases, they take the shape of the container. Similarly, volume, you can say that students, solids have fixed volume, whereas liquids and gases, they take the volume of the container. You can also say that students, volume of a gas is nothing but the volume available in the container where the gas can actually move around. The next property that we students have is compressibility. Solids have very low compressibility. Liquids have very small compressibility compared to that of solids. They have greater compressibility, but it is still very low. Gases, on the other hand, students, have very high compressibility. Diffusion. Now students, there is no translational motion actually available in solid particles. So you can say that there is no property of diffusion in solids. Liquids do have some property of diffusion, whereas gases, students, on the other hand, due to free movement available for gas molecules, they have a very high tendency of diffusion. Students, now moving ahead, the physical state is very much influenced by intermolecular forces of attraction between the particles. So the intermolecular forces of attraction or repulsion between the interacting particles are the intermolecular forces. Now students, we are going to study about a very important force which is called as van der Waals forces. Students, all the attractive forces that we are now going to study, these are also called as van der Waals forces. So the different types of van der Waals forces that we are going to study are, the first type is called as dipole-dipole interaction, which is also called as Keeson forces. Then we have dipole-induced dipole interaction, which is called as Debye forces. Then we have ion dipole interaction. Then we have dispersion or London forces, and finally hydrogen bonding. Among these students, we are going to study in detail the first, second, fourth, and hydrogen bonding. Students, though we've already done it in chemical bonding, I will still, however, give you an overview as to what exactly is hydrogen bonding. So let's start, student, with the first type of interaction that we have, which is called as dipole-dipole interaction. Now students, what exactly is a dipole? If I consider a molecule such as HCl, now students, we know that chlorine is much more electronegative as compared to that of hydrogen. So what really happens is the electron cloud, the electrons that they are sharing, that electron cloud is more closer to chlorine as compared to that of hydrogen. As a result of which, what happens? Chlorine develops a partial negative charge. The delta sign that we see over here, students, is a partial negative charge. And on the other hand, a similar magnitude but positive charge is developed on hydrogen atom. Such a molecule is called as a polar molecule because its polarity is developed over here. Now when such two HCl molecules, they come close to each other, what happens here, students, is you can see that there is a force of attraction between the two polar molecules. A force of attraction is generated between the two polar molecules, between the two dipoles, and this is called as dipole-dipole interaction. If let's say, if you try to understand HCl and I have one more HCl, I can have such many HCl molecules. So because of the development of partial positive and partial negative charge, we can say that there is an interaction developed. Now students, hydrogen bonding is also a form of dipole-dipole interaction. However, for hydrogen bonding, the bond should be between hydrogen and fluorine, oxygen and nitrogen to form a bond, which is hydrogen bond. Now students, hydrogen bonds are very strong as compared to the other forces. Yeah, continuing dipole-dipole interaction. Now students, the force of attraction over here in dipole-dipole interaction, so this dipole-dipole interaction force is inversely proportional to the cube of the distance between the dipoles. So if I have a stationary molecule, or for stationary dipoles, the dipole-dipole interaction, or the force of interaction, is inversely proportional to the cube of the distance between the interacting particles. You can say that here r is the distance between the interacting particles. I repeat, r is the distance between interacting particles. And students, for rotating dipoles, the dipole-dipole interaction is inversely proportional to the sixth power of the distance between the interacting particles. So this is for rotating dipoles. It's a very, very important interaction, students. Continuing with intermolecular forces, the next intermolecular force that we have shown is called as dipole-induced dipole interaction. So what exactly do we have here? The first case, students, we have a permanent dipole. We have something, let's say, like an HCl or like HF. Okay, it's a polar molecule which already has a partial positive charge and a partial negative charge. So you have a polar molecule, a permanent dipole. Now, students, let's say a non-polar molecule comes in close proximity of a polar molecule. Now, when I say non-polar molecule such as, let's say, a Cl2 or an H2 or N2 or let's say a noble gas, okay, they come in close proximity to a polar molecule. What happens here is the dipole, the permanent dipole, induces polarity into a non-polar molecule. So the non-polar molecule, which did not have any partial positive and negative charge, because of this interacting polar molecule, it develops partial positive and partial negative charge. It develops polarity, and then what happens is they develop an interaction with each other. This is called as dipole, which induces a dipole into another molecule. And even here, students, the dipole-dipole interaction force, the dipole-induced dipole interaction, I repeat, the dipole-induced dipole interaction is inversely proportional to the sixth power of the distance between the molecules. I repeat, it is inversely proportional to the sixth power of the distance between the molecules. Now, the next intermolecular force that we have, people, is called as dispersion or London forces. London forces, it's not that the force was discovered in London, it is given by a German physicist, okay, Fritz London. So what we have over here, students, is that here we have two non-polar molecules. Okay, so I repeat, both are non-polar. Let's say we can consider something like, let's say we have two helium atoms or two argon or krypton or xenon. Okay, we can take noble gases, take it, then non-polar. Now what happens is, due to the different types of motions which are present in every atom, we can say that for a very small fraction of a time, or one of the two non-polar molecule becomes an instantaneous dipole. It develops a polarity. There is an unsymmetry for a very small period of time in the amount of charges which are the charges are which are present in that particular atom. One particular side, you can say, that becomes more positive, the other side becomes negative. You can say that partial positive and partial negative charge is developed instantaneously for a very small period of time. Now what happens because of that? It develops, or it induces a dipole into another molecule, into the other atom or molecule which is present over here. And this interaction between the two is called as dispersion or London forces. Now, out of all the forces that we have studied, students, till now, this is the weakest, because the interacting molecules have to be around as close as 500 picometers. So the distance between the interacting particles can only be less than 500 picometers. And even here, the dispersion force or London force is inversely proportional to the sixth power of the interacting molecules. So please note that, students. Okay, I repeat, the interacting particles, I repeat, the interacting particles, okay, should be the distance between the interacting particles, pardon me, the distance between the interacting particles should be, students, less than 500 picometers. And at the same time, the the force of attraction between the interacting particles, we can say the force of attraction or London forces is inversely proportional, students, to the sixth power of the distance between the interacting particles. So these are the different forces. I repeat, students, there is one more: hydrogen bonding. I have made a detailed lecture on hydrogen bonding, which is also a very important. I'll share the link of the same in the description and also in the video. I want everyone to please go through hydrogen bonding. Next, students, what we have is thermal energy. Students, the intermolecular forces and thermal energy decides the physical state of the matter. Now, for example, students, if we consider solids, so we know that there is not a lot of motion, translational motion, or different types of motion available to the particles. And that is why, students, the potential energy of the molecules is very high, excuse me, as compared to the kinetic energy. On the other hand, students, when we consider gaseous atoms, there the thermal energy, the kinetic energy is very high as compared to the potential energy. And kinetic energy, students, is a function of temperature, it's a function of thermal energy. So we can say that higher the thermal energy in gaseous is the thermal energy is highest in gaseous state, and it is the lowest in solid state. So thermal energy also helps decide the physical state of the matter. So thermal energy, it is the energy which arises from the motion of its atoms or molecules, and it is directly proportional to the temperature of the substance. Kinetic energy, students, is due to thermal energy, whereas potential energy is due to intermolecular attraction. Now, if we consider, students, gaseous state, in gaseous state, students, the thermal energy is greater, much greater than the potential energy. And in case of solid state, students, the potential energy is much greater than the thermal or kinetic energy. In case of liquid state, the kinetic or thermal energy is greater than potential energy, not as great as as we have in gaseous state. So, if you look at intermolecular attraction, strongest intermolecular attraction, students, is present in solids compared to that of liquids, and it is the weakest in gas. Whereas on the other hand, in case of thermal energy, strongest thermal energy is in gases, and then liquids, and then solids. Next, students, we now move into gaseous state. Now, students, I've given all the characteristics of gaseous state. We've learned that in the first slide today, but certain measurable properties of gases. Which are the different measurable properties of gases, students? The first we have is mass. We usually measure mass, or we calculate the number of moles of gas. We usually do that in grams. Then we can also calculate, students, volume of gases. Now, students, volume, I repeat, is the you can say that the size of the container, because it is the area, it is the volume available for the gas molecules to move with the container. And then we say the volume of the container becomes equal to the volume of the gas. Pardon me, the volume of the gas is equal to the volume of the container. And similar, students, what exactly is pressure? Pressure is, so when gas molecules, they're rapidly moving in random directions, they collide with the walls of the container, and they exert pressure on the walls of the container. This pressure, students, is termed as the pressure of the gas. I've written various units, students, that we'll be using in this particular chapter for volume and for pressure. I've also written their particular conversions. Please make sure that you note this, because we need all this when we'll be doing numericals. So now let's get into the different gas laws that we have. Now, students, the first gas law that we're going to study is called as Boyle's law. Now, to actually measure pressure, we use something called as an open-ended manometer or a closed-ended manometer. I'll also make a separate lecture on that when we'll do sums on manometer. Now students, Boyle did various experiments and he made the following observations. Students, we can say that at constant temperature, I repeat students, we can say that at constant temperature, pressure of a gas is inversely proportional to its volume. I repeat, pressure of gas is inversely proportional to its volume. So we can apply the relationship that, let's say students, if P is the pressure of the gas, V is the volume of the gas, we can say that pressure is inversely proportional to volume. Now, in order to remove proportionality, let's introduce a constant. So we can say that pressure is equal to some constant K upon volume, where I repeat students, K here is nothing but your constant. Now students, from here we can see that the product of pressure and volume is a constant. Or if I change the pressure from P1 to P2, volume changes from V1 to V2, we can apply a relationship, students, that P1 V1 is equal to P2 V2. A very important relationship, students. Okay. Now, on the basis of this, we can have many plots. Let's try and plot some. If I want to plot, students, let's say pressure versus volume, we know that they're inversely proportional to each other. So we get a graph which is something like this. Okay, it's a rectangular hyperbola. Now, students, so this is the plot for pressure is inversely proportional to volume. Students, if I plot pressure versus 1 upon volume, I repeat, if I plot P versus 1 upon V, then students, we get a graph which is something like this. Because we can say that pressure is directly proportional to 1 upon V. Or though pressure is inversely proportional to volume, here we can say that pressure is directly proportional to 1 over V. Now students, if I plot this at different temperatures, similarly over here, let's say if I plot at different temperatures, I'll just change this a bit. Okay, and let's say students, this is at temperature T1, T2, T3, and this is, let's say, temperature T1, T2, T3. Then students, in both the case, we can say that temperature T3 is greater than T2 and will be greater than T1. Now students, we can have such various different types of plots. For example, let's say students, we know that PV is always going to remain constant, so you can have a plot for PV versus P. And PV versus P or PV versus V, students, the plot is going to remain the same because the product of pressure and volume is always going to remain a constant. So we'll get a graph which is parallel to the x-axis, and the same thing again, if I keep increasing the temperature, we observe that the plot moves higher. Eventually students, we can also, when we'll study ideal gas, we can also apply all the gas laws, all the plots, just using the ideal gas equation. Then students, we know that PV is constant. So if I take log on both sides, I get log P plus log V is log of some constant. Students, we know that log of constant is also a constant. Finally, I can write this equation in the form log P is negative log V plus log k, which is again a constant. This equation is of the form y is equal to mx plus c. Students, so y-axis we have log of p, x-axis we have log of v, and negative slope, and hence the students the plot would look something like this. Okay, so for homework students, I want you to try these plots and tell me how they would look like. I want you to plot for me P versus PV, okay, P or V versus PV, and students, you can plot a P by V, let's say, versus 1 by V. I want you students to try these two plots, and in your comments you can also tell me what will the answer be for these two plots. Okay students, now let's move ahead with the next law. The next law, students, that we have is Charles' law. Now according to Charles law, we have at constant pressure, okay, the volume of gas increases or decreases by 1 over 273 times its volume at 0 degrees for every 1 degree rise or fall in temperature. Let me give that law again, students. At constant pressure, the volume of gas increases or decreases by 1 over 273 times its volume at 0 degree for every 1 degree rise or fall in temperature. So students, from here we can say that if let's say V naught is the volume of the gas at 0 degree, then the volume of the gas at some temperature T degree will be volume at 0 degree plus T over 273 times the volume at 0 degree. Okay, so what can we do over here is, if I take V naught common, what we get over here is 1 plus T over 273, or this becomes 273 plus T over 273. And students, we know that 273, or to be very specific, 273.15 Kelvin is written as 0 degree Celsius. So this relationship, students, further can be written as velocity, volume at certain temperature T is V naught into T upon T naught. And students, here the temperature is in terms of Kelvin, or what we get over here is Vt over V naught is T over T naught, or volume is directly proportional to temperature. So another way of writing, students, Charles' law is that at constant pressure, I repeat, at constant pressure, volume of a gas is directly proportional to its temperature. I repeat, volume of the gas is directly proportional to its temperature. Now students, let's try and plot this, since we know that Vt is V is directly proportional to T. And let's say, students, if I'm plotting this in terms of degree, in terms of Kelvin, if the temperature is in Kelvin, I want students to remember, students, it's not possible to reach absolute zero or to reach 0 Kelvin. We can discuss that as a separate lecture as to why is that not possible. And that is why what you'll observe here, students, is that the initial plot is shown as a dotted line. Okay, and this is 0 Kelvin, and this is, let's say, students, at some pressure P. The same plot, students, if I want to do for the temperature, however, at in terms of degrees Celsius, volume versus temperature, and temperature in degrees Celsius, then the graph will start somewhere here. Let's say this point, students, is minus 273.15. Pardon me. So initial plot, and then you can draw it like this. So this is the plot in terms of degrees Celsius. Let's say if we do this experiment at different pressures, this is temperature, volume. I repeat, students, and let's say this is in terms of Kelvin, and if I do this at different pressures, let's say, students, this is at pressure P1, this is at pressure P2, and this is at pressure P3, then P1 is greater than P2 and is greater than P3. So these are the different plots, students, for Charles' law. The next law, students, that we have is called as Gay-Lussac's law. Now, students, with Charles' law, okay, I'll also give you a homework question. I want students for Charles' law, that students to try this particular plot. Let's say, students, V by T versus T. It's a very simple plot. I want you students to plot this V by T versus T. Okay, now, students, Gay-Lussac's law is just exactly like, you can say that Charles' law. However, in this case, it is constant volume instead of constant pressure. I repeat, it is constant volume instead of constant pressure. And we can write the same law, that at constant volume, the pressure of a gas increases or decreases by 1/273.15 times its pressure at 0 degrees Celsius. We can write all the same equations again. We can write all the same points. However, volume is to be replaced by pressure, and pressure is to be replaced by volume in the equations. However, students will still write the shorter form of the law. At constant pressure, pardon me, at constant volume, we can say that pressure of gas is directly proportional to the temperature of gas. Or, students, we can say that over here, P is directly proportional to T. Or we can apply the same relation, P1 upon T1, students, is equal to P2 over T2, which is another constant. And I want everyone to give me the different plots. I'll help you with one. ये PT का जैसे कि हमने एक plot बना दिया. The plot would look like this. I want all the plots जो हमने बनाए even for Charles' law, but they were all volume versus temperature. मुझे चाहिए आप pressure versus temperature के plots बनाए for Gay-Lussac's law. Now, the fourth law, students, that we have is called as Avogadro's law. Students, Avogadro's law states that at constant pressure and temperature, I repeat, at constant pressure and temperature, volume of gas is directly proportional to its number of moles. So let's say, students, if V is the volume of the gas, if N is the number of moles, so we can say that volume of the gas V is directly proportional to N, which is number of moles. So let's try and draw different plots again, students, for V versus N. We know that, like, let's say, to remove proportionality, we introduce some constant. So V will also be constant into N, where N is number of moles. So students, if we draw the first plot, let's say plot is between volume and number of moles. And we know that there is a direct proportional relation, so we can say that the plot would look like this. Students, if I give you this plot, I want you to answer this. Leave your answers in the comments. Let's say if I do this at let's say different temperatures, T1, T2 and T3, what will the relation be between them? Sure, let's try one more plot, students. If I want to plot V by N versus N. So we know that, students, if V is constant times number of moles, we know that, students, V by N will also be a constant. And since V by N is a constant, the plot would look like this. Similarly, I want you students to try this homework plot. Where we have log of V versus log of N. So if we have to plot, people, log V versus log N, I want you to give it a try and let me know how will the graph look like. And finally, students, we have is if we merge all the laws, that is, the first law we had, students, that pressure is inversely proportional to volume. I'll write it in a different way. I'll write volume is inversely proportional to pressure. This is Boyle's law. The second law, students, that we did was volume is directly proportional to temperature. This was Charles' law. The third law, students, we had, it was Gay-Lussac's law, where pressure was directly proportional to temperature. And the next law, student, that we had is volume was directly proportional to number of moles. This is Avogadro's law. Now, students, if we merge all of these laws together, we have the ideal gas law, where we observe here, we get that law is V is directly proportional to N into T over P, or we can say that PV is proportional to NT, or PV is equal to N RT, where R, students, is called as universal gas constant. I repeat, R stands for universal gas constant, and the value of universal gas constant, students, depends upon the unit of pressure and volume. I repeat, if we have to determine the value of R, we have to carefully observe what is the unit for pressure and volume. So I'll give the value of universal gas constant depending upon the unit for pressure and the unit for volume that we use. And I'll give you the most frequently used one. So for example, the value of R is 8.314 joule per Kelvin per mole, or joule Kelvin inverse mole inverse. We use this when students pressure is in pascals or Newton per meter square, and when the volume is in meter cube. The second unit of R, students, that we use very frequently is R is equal to 0.0821. Again, the unit is liter atmosphere Kelvin inverse mole inverse. This is the unit that we use, students, when the pressure is in atmospheres and the volume is in liters. Next next value of R is 0.083, and here liter bar Kelvin per mole, and we use this when the pressure is in bar and the volume is in liters. And finally, students, if we want to measure in terms of calories, so 8.314, if I divide, 8.314 by 4.188, we get this as 1.97. So the value of R is 1.97 when we want it in terms of calories per Kelvin per mole. So these are the different units of R. We need the different units of R, students, when we want to do numericals. So this was a basic introduction to the chapter along with all the gas laws. In the next session, we will start, students, with Dalton's law of partial pressure, followed by we will do Graham's law of diffusion. I hope, students, you really enjoyed and you understood the lecture. For any questions or any doubts, you can always leave your comments behind, and we will definitely get back to you. Thank you, students. Thank you for your time.